Hello and welcome to the YouTube channel Boiler Analytics by IndiaBoiler.com. As promised, we are now going to bring you some other discussions on boiler operation and maintenance. And I'm starting this new series of videos on analytical approach in O&M practices of boiler. This is the approach which I have taken during my long journey of around 38 years in this business, and it has given me result. So I wanted to share this approach with you, bringing various facets of uh, operation and maintenance difficulties that we face from day to day, and how to deal with those issues analytically. Now, most often I have seen that many of us who are in the O&M practices of boiler, they take the approach of this WWH. Now, what is WWH approach? That in any action that you take in your operation and maintenance, whether you are in operation, whether you are in maintenance practices. Now, any action that you take, you are about these three areas. First is when to take that action. Second is what actions to be taken. And third is how to carry out that, right? Now, the point is that this when, what, and how, this is even known by any good experienced supervisors. Then what is the point of being an engineer, right? You will be a competent engineer in boiler systems when you start asking the question, why to take that action? For every action, the reasoning should be there behind you, right? You have to ask this question in every aspect of your work. Why I do this? A pressure is to be maintained. Why it is to be maintained? If it goes up, what actions to be taken? Why it's to be taken? So every time you ask this question, why? And to learn why, you basically need the analytical approach. Now, what is analytical approach? What does it mean? Now, if you just look up the definition of analytical approach, it will tell you is the method, basically, is the method based on breaking down a complex process into small parts for the better understanding of the whole. If you want to understand thoroughly about something which is big, you cannot do it all at a time, right? So if you want to take a closer look, naturally you have to break it into small areas, then take a closer look, right? So that is what basically analytical approach means. Now, when you talk about the boiler system itself is a very, very complex system. It comprises of so many subsystems, and all these subsystems are also having so many components, right? And each of these subsystems and components, they have a specific objective to fulfill in order to, for the proper operation output of the system. Every subsystem, every component in this subsystem has to fulfill a specific objective, right? Now, each components to fulfill this objective, they are working following a basic engineering principle. Engineering theory is something you have to connect all the time, right? When I talk about practical operation or practical work, now what is the difference between a theoretical boiler and a practical boiler? So basically, in theory, everything is ideal. So you take a consideration, you take an assumption, that assumption is not getting deviated. So naturally, when it works, it gives a specific output based on that assumption. Now, when you are following a system, the system outputs in terms of various parameters, they will give you the idea to what extent things are working towards the ideal condition, right? Because uh, unfortunately, every component in actual world are working with a specific field limitations. Nothing is ideal in the practical boiler system. So if you are approaching analytically, a straightforward understanding, it is going to give you best result when it is reaching towards the ideal condition, right? So that is the basic approach we need to take. Now let me now first just give you a step-by-step approach towards the boiler system, how to become analytical, right? So to understand analytically the total boiler system, the first thing you do is you break the total system into various subsystems, right? So once you break into various subsystems and it's having its own components, then you take a closer look to that subsystem and then ask few questions. The first question, as I told you, that every component has a specific objective to fulfill. So first be clear about that. What is the objective? And not only what is the objective, to what extent it has to fulfill. For example, if I talk about a deaerator, the objective of a deaerator is the removal of dissolved oxygen from the feed water. But a mechanical deaerator has to remove the dissolved oxygen to the extent of 7 ppb, right? Now that is the extent of its work and it has to fulfill that work. If it doesn't, then the next one, which is taking care of the residual oxygen, that is hydrogen, it won't be able to do the job. So that is the basic understanding. If a component has a specific objective, it has to fulfill the objective. Now, in order to fulfill the objective, as I told you, it is following a basic engineering principle, right? So then you ask this question, which basic engineering principle does it follow to fulfill that objective? And once you know this, you know that what are the parameters that is going to indicate that it is working in an ideal condition. And then you will understand that, okay, what are the field limitations? Now, here comes the practical experience. If you know your system very well, if you know your system for a long time, right? So then you know that what are the limitations. Now, once you know this, then it will be easy for you to take a decision that, okay, what should I do so that I can reach towards the ideal condition? So there comes the why part. Why I'm doing it? I am doing it to reach towards the ideal condition, and these actions will take me towards the ideal conditions. It's not very complicated theory. It's not a very complicated approach. In fact, analytical approaches are never complicated. It is the simplest approach, right? So let us take a look at the boiler system. Okay. So I'm taking the subcritical boiler system, let us say 500, 600 megawatt power plant boiler unit. I'm taking a power plant boiler unit because it has got all the subsystems and components in it to have a proper discussion. So we have got the main plants, the boiler, the turbine, and the condenser. The first, the feed water is received from the condenser. The majority of the feed water is received from the hot well of a condenser. So from there, the boiler feed, the condensate extraction pump is basically extracting the condensate and taking it up to the deaerator. Now, in a high pressure power plant boiler system, there is anything in excess of 250 megawatt. The deaerator is high pressure deaerator. So the temperature of the deaerator is in the range of around 170 plus. Whereas the condensate which we receive from the hot well is in the range of around 45, 46 degree, right? So you require some preheating of this condensate. So that we are doing through LP heater from where the steam has been extracted from the LP stage of the turbine and heating this feed water. This is called a regenerative heating practice. It has got a thermodynamic advantage, which we are going to see later on. And this increases the temperature, something in the range of 140, 145, from 45 to 50 degree. It increases the temperature to around 145, 150, and then it goes to the derator, where the pegging steam, again, which is coming from the LP part of the turbine, is heating the water and doing the derations. From the derator, the water comes to the BFP. From the BFP, the water goes through the boiler system, through economizer, where it gets feed water gets heated and enters the drum. Again, in a high pressure boiler system, the drum saturation temperature is pretty high, in the range of around 350, 340, like that. So a derator outlet, which is in the range of 170, 175, 178, to reach anywhere near 320, 330, because that should be the temperature of the economizer outlet to get a better steam generation facility in the evaporator. So we require another heater before the economizer, and that is the HP heater, where the steam is being taken, similar to the LP heater. Steam is being taken to heat the feed water to a temperature of around 240 to 50 degrees centigrade before it goes to the economizer, and then it gets heated from 240 to 50 to 310, 320 degree and enters the evaporator. In the evaporator system, the heat is used to generate the steam in the evaporator system in the water walls, and that steam is being separated from the drum and goes to the steam system, where we are having the superheaters. In most cases, there will be a convection superheater. Then there will be a couple of superheaters. There is platen and final superheater in the furnace itself. Platen final superheater will be most likely location will be above the gooseneck, and the main steam at a pressure of around 150, 160, 180 kg per centimeter square, with a temperature of around 540, 550 degree, goes to the HP part of the steam turbine. In a high pressure system, power system, the turbine is having two parts. One is the HP part of the turbine and another is IPLP part of the turbine. In HP turbine, the steam is getting expanded to a pressure of again around 30 to 30 kg per centimeter square and a temperature of around 300, 320 degrees centigrade. And then that exhaust steam from that comes back to the boiler. But to maintain the main steam temperature, we have got that temperation spray. Sometimes it is two stage, sometimes it is single stage temperation, and the spray is coming from the BFP discharge, sometimes the HP heater outlet, most of the times nowadays. The HP exhaust comes back to the boiler and gets reheated from 300, 320 degrees centigrade to again 530, 540 degrees centigrade, similar to the main steam temperature, and goes to the IPLP section of the turbine. The reheater temperature, which I think most of us know, that which is not desirable, but it should be there to maintain the temperature. The reheater temperature spray is usually taken from the intermediate stage of the BFP because it doesn't require that much pressure. It's only 32, 33 kg per centimeter square pressure here. There will be two sets of reheater. One is called the cold reheater, another is called the hot reheater, or primary reheater and secondary reheater and finishing reheater. The steam from the IPLP section of the turbine will be expanded to the condenser vacuum pressure, and where the steam is going to get condensed and goes back to the system. Similarly, we will have various other systems. For example, we require the fuel system. In a pulverized coal-fired boiler, it usually starts with where the coal is being coming from the rakes, right? So there can be a track hopper or there can be a wagon tippler, and from there it goes to the crushers, and after that there will be the stacker reclaimer, and from there it comes to the coal bunkers, the silos, right? From the bunker, to the rotary feeders, and this feeders feeds the coal to the pulverizers, which basically pulverizes the coal. From the pulverizer, the coal is being lifted to various elevations of the burner in the furnace. Taking a look at the combustion air system, usually there will be a FD and primary air fan. Now, the primary air fan air will come to the pulverizer, whereas the secondary air, usually supplied by the FD, will go to the wind box directly to the furnace. And then we have got the flue gas system, where the flue gas will be taken first through an ESP, where the major fly ash should be separated from the system. Then the ID fan, which is creating the negative suction of the system, and then to the chimney. Nowadays, of course, you will get another component for a 500, 600 megawatt unit, and that is called an FGD, flue gas desulfurization system. Now, if I talk about the additional system, yes, of course, you will have some chemical dosing system. Some chemical dosing is done at the CP outlet, condensate extraction pump outlet. With almost every system, you will have a dosing system after the derator. And in some old system where the conventional phosphate hydrogen dosing system is going on, there will also have an HP dosing that is on the in the drum. And you have got around 0.5 to 0.6% makeup water that will be required to make up the water, because not the total quantity of water is received from the condensate. Some amount of water will be lost in this way or that way. So the makeup water is being taken from the MB outlet. Right? So this is the total system, which I can say the boiler system. Now you can understand this boiler system is having so many subsystems. For example, we have got the feed water system, boiler feed water system from the condensate extraction pump up to the drum. Then we have got the circulating water and steam system in the evaporator. Right? Likewise, we can have the fuel system, the combustion air system, the flue gas system, steam system, ash handling system, all such systems will be there. Now, what we intend to do is individually take one system and take a close look at that, right? Close look at the components. Ask these three questions. What are the objectives? What basic engineering principle it is following? What should be the ideal parameters? And the most important thing, what are the limitations? If it is not reaching the ideal parameters, why it is not reaching the ideal parameters? So what are the limitations in our system? So this is the approach I'm going to take in my subsequent videos. I'm going to bring up few facets of operations. For example, let us say what should be the way of doing a smart soot blowing in our system, and such things, not only in operation practices, not from only the performance point of view. I would also focus in some areas from the reliability point of view, because that is what we do. We offer consultancy and training services on both performance as well as reliability. So with that, I'm ending this particular session. You can look forward to our next video in this particular series, which I'll try to bring as soon as possible. Thank you very much. Bye-bye.